Welcome to Real Learning Center. So we are going to go to the second session of our topic on light. So we completed reflection and refraction. We got a fairly good understanding of various natural phenomena which happen and what are the laws of reflection, laws of refraction. Now we are going to get into dispersion and slightly touch upon interference and diffraction. So if you look at this rectilinear proportion of absorption of light, reflection, total internal reflection, all that is over. Now we are going to touch in this session only mainly dispersion and slightly on interference and diffraction, which needs to be separately studied. So this will give an introduction to that. So let's start with understanding how dispersion is simply another effect of refraction itself. Let's say we studied refraction and we saw that light enters from one medium to the other medium, then it bends from rarer to denser, it bends towards the normal, denser to rarer, it goes away from the normal, and we call what is called as refractive index as the ratio of the speeds between in the medium. All that we have seen. Okay. Now, one question we can ask at this point, which is, do all colors bend equally? In the sense that whatever the light I send here, let's say I want to send red color, and then I want to send violet, I want to send green, orange, all these colors, do they bend equally or do they bend differently? That is the question. Okay. To study that, we have to understand one important, that is, what are the of uh, speeds of different colors? Do they differ or is it same? So let us see that. So now first important thing to understand that is, if you look at light as in white light, it travels at 300,000 kilometers per second, which is like 3 into 10 to the power of 8 meters per second. So this speed, when we say, it is in vacuum. Okay, and sometimes we say air, but very thin air, as good as vacuum. So this 300,000 kilometers per second is exactly same for all colors. Hence, white color, which containing all colors, travels at a single speed. But if I actually take the light ray and make it go through, let us say, a glass slab. Okay. So first of all, we know that the light itself contains all these colors, though they are actually together. Basically, we can see that as only white light that actually contains so many colors. Now, when you put that into, they are all going at the same speed, and hence it is always white light. If there were different speeds, we would see a mix of different colors, different variations of the mixes, and see various colors. But it is not the case. Sun is white all the time. So if you put that in glass lab, then suddenly you can see that the light speeds are actually different. The red light is basically the fastest, and the slowest is the violet light. In most of the glasses. Okay, this is not like true for everything. Okay, it is not just about density. It is about how the light, different colors of the light interacts with the matter. Because vacuum is there is no matter, so they don't interact with anything, and they all go with the same speed. The moment they enter a medium, they interact with the atoms and molecules inside the matter, and how they interact depends on what the matter is. Okay, various colors have basically they interact very differently for various matter. For in the case of glass, most of the glasses we see that red actually travels faster and the violet the slowest. But it is not a norm. You can find a transparent medium in which red actually travels slower. So it's possible. Okay, it depends on the kind of material. But in most of the glasses, this is what we have observed. So when this happens, we can then say that refractive index of glass is different for different colors. Because what is refractive index? Refractive index is nothing but speed of light in vacuum divided by the speed of light in that medium. In this case, we see that the speed of light in the medium is different, whereas in the air they are all same. So the ratio will be different. Hence, refractive index will be different for different colors. So what does it do for us? What it does is the different colors now bend differently, the different angles. It has been seen that refractive index is more, it bends more. If it is less, it bends less. So suddenly we can now see that where the different colors actually bend with different angles. So what does it do for us? You could, let's say you take glass and air, and let's say you take white light containing all the colors. White light containing all the colors. Then again we draw a normal to find out basically what it does. Now if you see how it refracts, the red light actually goes the least refracted, okay, and because it is faster one gets the difference between its speed in water and in air is lesser, okay, because it is faster, whereas the violet is the maximum difference, so it bends more, okay. Whereas you can see that the orange and the greens and finally in the end actually the violet. So all of them actually bend with varied angles, and violet being the least angle. Okay, it's the maximum deviation, maximum deflection. So R is smallest. So R is measured from the perpendicular normal. So it is the smaller value of R. So you can very clearly see that refraction separates the colors. So whenever the white color comes into the medium, it actually separates just by simple refraction. But you know, the separation is actually not too far away from each other. Our eyes cannot actually distinguish too much. We still see something happening there, but we don't see different colors coming there. That's why we don't call it as dispersion yet. So we call this as just refraction only. Okay. However, if we actually construct this glass in a different way, like a prism, where there is an angle like this, and in two places it deflects, when it is entering, when it is getting out. In both places it gets separated. So when it gets separated more like that, you can see beautiful colors. So these colors basically were already there in the white light, but we were seeing only white. Now they are separated physically, and you can see them as different colors. So the first guy who actually showed this was Sir Isaac Newton. He showed that white light actually contains all the colors. And when people didn't believe, see, he said that maybe prism is doing something about it. Prism is giving its own color. So then he said, okay, let me do one thing. I will put two prisms like this. You can see the white light separates them. With one prism separates it, another prism combines it back to white light. They have put it in opposite direction. So he says that it was actually there in the first place with the white light. So he showed in the double prism very clearly how it gets combined back. So double prism is simply nothing but some kind of a glass slab if you join them together. So in a prism you can get the white light separated into its constituent colors. So what are those colors? So the colors are what we call Vibgaya colors. They are starting from violet to red, and red bends the least. You can see red actually bends the least. It is the fastest, and the violet bends the maximum. So this is basically how what we call rainbow color happens. So you can actually see that we can actually measure something called as an angle of deviation. Okay, so to just make it a little more rigorous to understand. So let's take a prism. Okay, and the prism is ABC, and the top angle, what we call as angle of the prism, is A. Okay, so it need not be an equilateral all the time. So you can have different angles. So this angle we'll call it as A. So now if you actually get a light to pass through this, one light ray comes here, and you draw, for example, a normal. and you know it bends towards the normal. Okay, so when this is an incident ray and this is the angle of incidence, and you can see that it bends actually towards the normal. Yeah. When it does happen like that, it goes inside and then it touches the other side too. Okay, this angle, let us say, is R1, okay, I1 and R1, refracted angle. So sin I1 by sin R1 is the refractive index of the glass. Okay. Now once it hits the other side, again it bends because of the change in the, this time it bends away from the normal. And when it bends away from the normal, let's say its incident angle itself is R2 and it bends away from the normal, we call it as emergent ray, incident ray, emergent ray, because it's going out, and we call that as I2. Okay. So once you have these things, we have introduced a new term called angle of deviation. What does that mean? That simply means it's like lateral shift that we studied. Here, if you actually have, if you did not have the prism, then it would have actually moved like this, the light, isn't it? Now it is moving like this. So if you want to find the angle between this line and this line, with the prism, without the prism, okay, with the prism is emergent ray, without the prism is this dotted line. So you can actually produce it back and get the angle there. This angle, we call it as angle of deviation, and this is given by a Greek letter delta, written like that, or you can read the English letter capital D. So you can use any one of them, and it's called angle of deviation. So this angle of deviation, if you use geometry and find out, actually you can find out using the simple geometry of the triangles. If you are good at triangles, you can do this. So this is actually, you can find out this angle of deviation D is equal to, okay, I1 plus I2 minus A. Okay, I1 is this, I2 is that side. So angle of incidence, angle of emergence, minus angle of the prism. If you do that, that will give you the D. But remember that the I2 is again dependent on I1, because I2 is emergent ray and it is dependent on the refractive index and the angle R2, because sin I2 by sin R2 is also refractive index, and sin I1 by R1 is refractive index. So you can compute I2 given I1. Okay. So we will say basically for minimum deviation, if you want to get minimum deviation when you are doing this, you have to put it I1 is equal to I2. This also can be proved. I1 is equal to I2 is for minimum deviation. That means if you actually take I1, okay, and increase it from 0, so keep on varying it, okay, and then angle of deviation will go on reducing and it reaches a minimum value. You can see I am plotting here actually angle of deviation on y-axis and the angle of incidence on the x-axis. So as you go further and further, then the angle of deviation decreases, and at a point angle of deviation is minimum. Here you can see minimum, and then it is going up again, means angle of deviation again increases. So you can, many problems you can actually solve by knowing the minimum angle of deviation is when I1 is equal to I2. So that is the point, the bottommost point is basically I1 is equal to I2. So this is basically one of the important aspects of prism that you need to understand. What is the angle of deviation if you want to compute? You can use this. Now, let's understand rainbow. More interesting thing is rainbow. So in a rainbow, how does rainbow happen? Is there a prism there? There is no prism actually. It's a raindrop. Assume that this is the raindrop, and I have actually blotted it up. Very small raindrop, very small. So it's not a big raindrop. This is actually not when rain is falling. It's almost in a droplet, kind of a vapor of water. It's there here, small droplets in between the air. So when that happens, the white light enters inside. Okay, when it enters inside, it is going from a rarer medium to denser medium. So it simply goes through a simple refraction. And then when it hits the other side of the droplet, okay, now it is going from water to air, which is going from denser to rarer medium. And if this is so small that these angles generally are more than the critical angle, and hence what happens, the light actually returns, light basically reflects. And when it reflects and hits this side again, it is going from denser to rarer, but this time it is normal refraction and it goes away. But please understand that the speed of light inside the water is different for different colors, like glass, and hence all these single, you can see very clearly that all the different colors are actually separating out, and more they separate out when they take a deviation, they take a total internal reflection and come out. Yeah, and you can very clearly see that red comes most bottom here is the red, and then afterwards the remaining colors, and the topest most is the violet. So this is how basically the rainbow happens. But you have to understand that it is not one single droplet. It is millions and billions of small droplets giving you little of light, and that light actually finally adds up in your eyes, and you can see the different colors. If you actually watch the real rainbow, okay, let's say you watch the real rainbow, what do you see? A beautiful rainbow. But you take a slight, give some, observe this a little bit. You can see here that the red light, actually red color, is on the top and violet in the bottom. But you have seen in our previous slide very clearly that red is at the bottom and violet is at the top. So what is wrong with our explanation? Why is red at the top? So that is the question. So how can you explain this? The interesting question to explain. Either your understanding is wrong or our explanation is wrong. Because our observation says that red is on the top. So what do? So we try to understand it like this. Okay. So let's say what nice thing about this is that when you are standing and watching water drop, the light from the water droplets, okay, you can see that there are multiple droplets. Each one of those droplets are giving you light. Okay. And it so happens that whenever whatever light comes in your direction to your eye, that is the only thing you can see. You cannot see the light which goes on the top of your head or bottom somewhere. What comes to your eyes is what you can see. From one single droplet, when it basically goes as a dispersion, and it comes out with separated light, that all the light that comes up one droplet we can't see. So we will see that the one droplet, let us say if you see this bottom droplet, we can see the violet one. Okay. But the red one is going down, we can't see that. Now, but we can see the red of the droplet which is above that, because that is coming towards you. So whatever you see here very clearly, that the red is coming from one drop and violet is coming from a different drop. Both of them are coming to your eyes, and hence red actually you can see on the top. And what is surprising also is that a person who is standing there somewhere else can see that. Okay, he is seeing the red of the drop for which you are seeing the violet. So he sees the violet of the next drop below that. So he actually is seeing a different rainbow than what you are seeing. So that is how rainbow works. So though in the case of a single droplet, the red is at the bottom and violet is at the top. When they are mixed like this, what comes to your eyes, that particular deviation what it takes, there you see the red at the top and violet at the bottom. So that is the secret of rainbow. Okay. Now let's look at new things. we will want to talk about interference. What is this interference? So you see the color of a soap bubble looking so beautiful. Yeah, this is basically because of interference. And this interference, how does it happen? You cannot explain it using what we consider light to be a simple rays. Okay, lights are not simple ray kind of things. So light behaves very, very peculiar. To be able to explain this, you should consider light as waves, like water waves. You have seen light as waves. Only then you can explain why this happens. So it is supposed to be like this. The light actually is like a wave. Okay, and every color is a different kind of a wave, in the sense that the frequency of movement like this is different for each color. Okay. That is why they are different colors, because they have different wavelengths, they have different frequencies. So when you studied wave, you know about frequency and wavelength. They have different wavelengths, different frequencies, hence they are different colors. Now, such a wave, when the white light falls onto that, it contains all the colors. So now what will happen? Let us actually take this and magnify it. What part? The soap film. If you see the soap film on the soap bubble, it is like a micron thick. It is extremely small. The thickness of the layer of the soap film is so small. When the light enters to that, what will happen? Let's see this. So I am taking two rays of light entering. Now you see that these two rays, when they are entering the light, entering inside. This I have shown here as a big chick. This one like this is nothing but the very thin layer of the micron. So when the light enters, it actually goes from air to water medium. That's water, soap water. And when that goes there, it bends towards the normal. And then when light finally goes from the other side into the bubble, uh, there it is going from denser to rarer, and there is also a reflection because. So that reflection gives rise, that reflected light again. See this XO, there's the light going, and OY is reflected, and that OY light gets out again through refraction. Now, if you consider, for example, light as a wave, then depending on how much they have traveled inside that soap film, it is possible that the light which comes out actually are separated at different phases. In this case, what is happening, you can see that both of them are coming perfectly aligned. So when they come out perfectly aligned, when this is going up, the other one is also going down. Up. This is going down, other one also is going down. Then it's called in phase, perfectly aligned. So when they are perfectly aligned, we call it as constructive interference. That means a particular color which is for which this is happening actually looks brighter, more of that particular color, constructive interference. Whereas it is possible that inside the thickness is such that for a given color, okay, it doesn't come out like that. It comes out in opposite phases. That means both of them go inside. When they come out, actually, one is in opposite. See, it all depends on how much distance it has to travel inside. Depends on the thickness of this the layer of the soap bubble. So how many waves can be accommodated inside that? So depending on that, what comes out actually can be in the opposite phase. That means if one of them is going up, other may be going down at the same time. So what you see outside is the addition of these two. So when you add these two, actually you will get 0. That means that color which goes through, for which the thickness is such that it exactly takes that integral numbers in such a way that what comes out is actually in opposite in phase with each other. When such a thing happens, we call it as a destructive interference. That means they interfere each other in the opposite phase. If you go like this, it is constructive. If you go like this, it is destructive. Okay, that's a destructive interference. When that happens, that particular color you can't see. Now you can see in the bubble what happened was white light entered. For some light, the thickness was such that for some colors, they went through a destructive interference, or some colors went through a constructive interference. That means in the white light constitutes many different colors. If they are in the correct proportion, you see it as white. If they are in different proportion, you don't see it as white. You see, I see that color more. So that is what happened. Some of them were actually removed, some of them were enhanced. Hence, you look at it as a nice colored soap. So this is called interference, and we can actually do a lot of study on interference and understand the wave nature of light. So one more phenomena that we want to talk about is the diffraction of light. So what is this diffraction of light? So let's say there is a parallel ray of light coming here. So there are parallel rays. Let's say I'm able to send some parallel ray of light, and I will put basically an obstacle to the light with a small slit inside, and then I'm going to basically put a screen on the other side. So when that happens, this light, when it goes through this, what do we assume will happen? What is our expectation? We know that light travels in straight lines. So what is our expectation? Our expectation is that the light goes through the slit and creates, actually, light goes through the slit and creates a small image, small light lit up there in the middle of the screen. So this is what we expect, but it's not what is going to happen. So what is going to happen is the light actually spreads like this, and you can see a lot of illumination of light, though the light does not actually have exactly the same amount of light everywhere. It just is basically spread out. So it tells us very clearly that light here is actually splitting, not splitting, only deflecting. The light actually is deflecting, in the sense that in the edge, towards the edge, light is bending. There is no change of medium here. If there is a change of medium, it is called refraction. Here, bending of light at sharp edges is called as diffraction. In sharp edges, light bends. So wave theory of light can explain this, why it bends. In sharp edges, it bends. In fact, sound also does that, the diffraction of sound. So if you, it doesn't need such sharp edges. If you are actually, if somebody is speaking on the other side of the wall, you can still hear because the light comes around, the sound comes around, but light doesn't come around. Light comes around only if there is a sharp edge. So because its wavelength is very, very small. We will understand this a little better when we go into the details of how diffraction happens and what theory can explain that. So light has so many such secrets, which is not very easy to unravel. So when you, let's go slowly and try to unravel one by one. So this now basically gives you an understanding of what is so see that we talk about basically when you talk about diffraction, you talk about not waves but about waves, and you say it is like some wave moving here, and through that when it goes, that wave spreads like this. So, and if it is actually a very small slit, the spread is actually more, and if it is actually a bigger slit, the spread is less. So this is the beauty of diffraction of light. So now let us actually concentrate on basically again coming back and looking at refraction in terms of spherical mirrors and lenses in the next session, and interference diffraction can be taken up a little bit later when we get into the nature of light. So that comes us to the end of the second session. Thank you.